All right. I'm so excited to be here with you, Ray.
It's great to be here. Great to see everybody together.
Yeah.
Beautiful audience.
So my favorite thing in that introduction of you was that you have been working in AI longer than any other human alive, which means if you live forever, and we'll get to that, you will always have that distinction.
I think that's right. Marvin Minsky was actually my mentor. If he were alive today, he would actually be more than 61 years. So. And we're going to bring him back also.
So maybe I'm not sure how we'll count the distinction then. All right, so we're going to fix the audio. But this is what we're going to do with this conversation. I'm going to start out asking Ray some questions about where we are today. We'll do that for a few minutes. Then we'll get into what has to happen to reach the singularity, so the next 20 years. Then we'll get into a discussion about what the singularity is, what it means, how it would change our lives. And then at the end, we'll talk a little bit about how, if we believe this vision of the future, what it means for us today. Ask your questions. They'll come in. I'll ask them as they go in the different sections of the conversation. But let's get cracking.
Can you hear me?
You can't hear Ray. Well, this will be recorded. You guys are going to all live forever. There'll be plenty of time. It will be fine. I'm just going to get started. I assume the audio will get worked out. They do a fabulous job here at South by.
I think they should be able to hear me and you.
All right, we got this over on the right. Audio engineers, are we good to go? We're good to go. All right. All right, first question, Ray. So, you've been working in AI for 61 years.
Oh, wait, can you hear me? Let's not.
So everybody in the front can hear you, but nobody in the back can hear you.
Can you hear me now? Okay.
All right.
I'll speak louder.
First question. So, you've been living in the AI revolution for a long time. You've made lots of predictions, many of which have been remarkably accurate. We've all been living in a remarkable 2-year transformation with large language models, a year and a half. What has surprised you about the innovations in large language models and what has happened recently?
Well, I did finish this book a year ago and didn't really cover large language models, so I delayed the book to cover that. I was expecting that to happen like a couple of years later. I mean, I made a prediction in 1999 that would happen by 2029. And we're not quite there yet. But we will. But it looks like it's maybe a year or two ahead of schedule. So that was maybe a bit of a surprise.
Are you predicted back in 1999 that a computer would pass the Turing test in 2029. Are you revising that to something more closer to today?
No, I'm still saying 2029. The definition of the Turing test is not precise. We're going to have people claiming that the Turing test has been solved, and people are saying that GPT-4 actually passes it, some people. So it's going to be like maybe 2 or 3 years where people start claiming, and then they continue to claim, and finally everybody will accept it. So it's not like it happens in one day.
But you have a very specific definition of the Turing test. When do you think we'll pass that definition?
Well, the Turing test is actually not that significant, because that means that you can, a computer will pass for a human being. And what's much more important is AGI, automatic general intelligence, which means that it can emulate any human being. So you have one computer, and it can do everything that any human being can do. And that's also 2029. It all happens at the same time. But nobody can do that. I mean, just take an average large language model today. You can ask it anything, and it will answer you pretty convincingly. No human being can do all of that, and it does it very quickly. It'll write a very nice essay in 15 seconds, and then you can ask it again, it'll write another essay, and no human being can actually perform at that level.
Right, so you have to dumb it down to actually have a convincing Turing test.
To have a Turing test, you have to dumb it down.
Yeah. Let me ask the first question from the audience, since I think it's quite relevant to where we are, which is, Brian Daniel, is the Kurzweil curve still accurate?
Say again?
Is the Kurzweil curve still accurate?
Yes, in fact, can they see that?
Let's pull the slides up. First slide.
So this is an 80-year track record. This is an exponential growth. A straight line on this curve means exponential curvature. If it was sort of exponential, but not quite, it would curve. This is actually a straight line. It started out with a computer that did 0.0000007 calculations per second per constant dollar. That's the lower left-hand corner. At the upper right-hand corner, it's 65 billion calculations per second for the same amount of money. So that's why large language models have only been feasible for 2 years. We actually had large language models before that, but it didn't work very well. And this is an exponential curve. Technology moves in an exponential curve. We see that, for example, having renewable energy come from the sun and wind, that's actually an exponential curve. It's increased, it's gone, we've decreased the price by 99.7%. We've multiplied the amount of energy coming from solar energy a millionfold. So this kind of curve really directs all kinds of technology. And this is the reason that we're making progress. I mean, we knew how to do large language models years ago, but we're dependent on this curve. And it's pretty amazing. It started out increasing relay speeds, then vacuum tubes, then integrated circuits. And each year, it makes the same amount of progress, approximately, regardless of where you are on this curve. We just added the last point, and it's, again, we basically multiply this by 2 every 1.4 years. And this is the reason that computers are exciting, but it actually affects every type of technology. And we just added the last point like 2 weeks ago.
All right. So let me ask you a question. You know, you wrote a book about how to build a mind. You have a lot about how the human mind is constructed. A lot of the progress in AI systems are being built on what we understand about neural networks, right? So clearly our understanding of this helps with AI. In the last 2 years, by watching these large language models, have we learned anything new about our brains? Are we learning about the insides of our skulls as we do this?
It really has to do with the amount of connections. The brain is actually organized fairly differently. The things near the eye, for example, deal with vision. And we have different ways of implementing different parts of the brain that remember different things. We actually don't need that. In a large language model, all the connections are the same. We have to get the connections up to a certain point. If it approximately matches what the brain does, which is about 1 trillion connections, it will perform kind of like the brain. We're kind of almost at that point.
Wait, so
GPT-4 is 400 billion. The next ones will be 1 trillion or more.
So the construction of these models, they are more efficient in their construction than our brains are.
We make them to be as efficient as possible, but it doesn't really matter how they're organized. And we can actually create certain software that will actually expand the amount of connections more for the same amount of computation. But it really has to do with how many connections a particular computer is responsible for.
So as we approach AGI, we're not looking for a new understanding of how to make these machines more efficient. The transformer architecture was clearly very important. We can really just get there with more compute.
But the software and the learning is also important. I mean, you could have 1 trillion connections, but if you didn't have something to learn from, it wouldn't be very effective. So we actually have to be able to collect all this data. So we do it on the web and so on. I mean, we've been collecting stuff on the web for several decades. That's really what we're depending on to be able to train these large language models. And we shouldn't actually call them large language models because they deal with much more than language. I mean, it's language, but you can add pictures, you can add things that affect disease that have nothing to do with language. In fact, we're using now simulated biology to be able to simulate different ways to affect disease, and that has nothing to do with language. So they really should be called large event models.
Do you think there's anything that happens inside of our brains that cannot be captured by computation and by math?
No. I mean, what would that be? I mean,
Okay, quick poll of the audience. Raise your hand if you think there's something in your brain that cannot be captured by computation or math, like a soul. All right, so convince them that they're wrong, Ray.
I mean, consciousness is very important, but it's actually not scientific. There's no way I could slide somebody in and the light will go on. Oh, this one's conscious. No, this one's not. It's not scientific, but it's actually extremely important. And another question, why am I me? How come what happens to me I'm conscious of, and I'm not conscious of what happens to you? These are deeply mysterious things, but they're really not, it's really not conscious. So Marvin Minsky, who was my mentor for 50 years, he said it's not scientific and therefore we shouldn't bother with it. And any discussion of consciousness he would kind of dismiss. But he actually did, his reaction to people was totally dependent on whether he felt they were conscious or not. So he actually did use that. But it's not something that we're ignoring because there's no way to tell whether something's conscious. And that's not just something that we don't know and we'll discover. There's really no way to tell whether or not something is conscious.
What do you mean? Like, this is not conscious, and the gentleman sitting right there is conscious. I'm pretty confident.
How do you prove that? I mean, we kind of agree with that humans are conscious. Some humans are conscious, not all humans. But how about animals? We have a big disagreement. Some people say animals are not conscious, and other people think animals are conscious. Maybe some animals are conscious and others are not. There's no way to prove that.